morning everybody. It's a cold weather today. It's raining outside. Okay, the topic today will be on chapter 6, work, energy and power. Okay, the first part of this we will deal with the different types of energy that we'll be covering in this chapter. Okay, the basic front line. Okay, before we look at different types of energy, we need to know the definitions. Okay, the definition that we have here is the standard one that you will find in your textbook. Okay, just take note of it. And the SI unit for energy is in joules, capital J, and the scalar quantity because energy, like we all know, only has magnitude. There's no direction. It's just a number, whether you have it or you don't have it, increase or decrease. Okay, there's no particular direction capping to it. Okay, the type of energy that we are dealing with, okay, is listed here. Okay, for O level, generally we will cover number 1 to number 5. Okay, in our 2-year syllabus. The first year we will actually cover number 1 and number 2 in detail. Then after that, number 4, thermal energy. Number 3, electrical and light. Usually we deal with the second half of the study, which is the year 4. Okay. Now for year 3, we will deal very in depth at potential energy. We'll look at what is potential energy, particularly at GP, what we call gravitational potential energy. We'll dwell in detail later on, including the calculations, and we also deal with the calculations of kinetic energy in details. Okay, things to take note: for potential energy, we cover a few types of potential energy. Okay, so if you are looking at identifying the energy, we really need to write down the full name for it. So you just can't write potential energy. You need to identify whether it is elastic potential, gravitational potential, or chemical potential. Okay, so let's take a further look at these energy. What do they make of? Okay, for kinetic energy, we are looking at energy due to velocity or due to motion. We always call this energy due to motion. Okay, if I'm moving, you definitely have kinetic energy. Okay, same thing. Energy can be used to work. It depends on what's your motive or what's your aim or what's your objectives. Okay, so there are various type of devices that we can make use of different forms of energy. For potential energy, we have chemical. Usually common one would be a battery. Okay, stored in as your cells or this. And your elastic potential energy, common one will be your rubber. The energy you gain when you are stretching an item. Followed by, you have the last one, your gravitational potential energy, the energy gain when you are looking at different heights of the object. Okay. The next form of energy we are looking for, okay, will be the converting of energy. Energy exists in different forms. We have talked about potential energy, we talk about kinetic, electrical, and so on and so forth. So how do we make use of energy to work? Primarily, the main reason that we are able to do that is because of conservation of energy. Okay, whereby energy are not created or destroyed, it's actually converted from one form to another form. So the words in red are what we call the keywords, where you are identifying the principles. Okay, so for students who are doing it for exam purpose, okay, please take note of the words in red. Okay, you need to so-called write them down or regurgitate them when you're looking at the questions. Okay, answering towards the question, but you have to keep these words inside your answer. Okay. Now, one classic example of conservation of energy, whereby one form of energy, here we are looking at kinetic energy, is actually converted to another form of energy. We will talk about electrical, okay, by the devices, okay, dynamo, okay, whereby this is what we call the motor, okay, whereby your action actually is converted to another type of energy, electrical, and from there the energy is actually further converted to other forms of energy that is required. For example, for if you're looking for light bulb, you'll be for light energy. Maybe I got a bit of thermal energy, that is heat generated, and maybe in the process of converting or in the process of using it, I actually generate sound. Okay, so you find that the 20 joules are actually converted. Okay, just that you may not get 100% conversion. Example, you might not get all the 20 joules converted to the exact energy that you want. You don't get 20 joules of light energy here because the energy, certain parts or certain components of the devices uses other form of energies. So principle of conservation does exist in throughout the system. It's just that you need to identify what system are you looking at. Okay, is it between the car, bicycles, and the wheel itself, or is it after the wheel, after the motor, to the light bulbs? Okay, so it depends on which system you're looking for. Okay, so conversion stages are different, but the amount that we are looking at is always fixed. 20 joules is being converted. Okay, the one that we have is the classic example is a pendulum, swinging of pendulum to illustrate different form of energies. The most common one is when you pull the pendulum, let's say to the side, okay, to the left side. Okay, there's a height being raised. Okay, we call this x meter. Remember, when we talk about height, vertical height, okay, we are actually looking at gravitational potential energy. So that's why I listed keywords for gravitational potential energy. I will pack it with vertical height, which means that if you are answering, let's say for students who are answering, looking at exam, you are answering the providing answers for the markers, whenever you mention gravitational potential energy, take note that you have to mention vertical height in your answer. You have to tell the marker what is the vertical height that you are identifying and what is the relevant gravitational potential energy, because these keywords are clues to tell the marker that the students, which like yourself, actually knows what the concept is about. Okay, and likewise, similarly, when you release the pendulum, it starts to swing down all the way to the bottom, and you commonly know, and most of us will know, that at the lower section here, the velocity is actually the highest. Okay, it's actually maximum. And you know that and from there you know that kinetic energy due to motion, you'll find that the velocity is max, the motion is maximum, the kinetic energy will be maximum. Okay, but how do you illustrate this understanding to the marker? Okay, to tell them, to show them that you actually know what is kinetic energy, you actually pack certain keywords to it. Okay, and the keywords that we're looking out for kinetic energy is velocity. In your answer, you must mention certain velocity, the speed, whether it's maximum, minimum, or even half, okay, to illustrate your understanding for the magnitude of kinetic energy. Okay, so same thing when we talk about conservation of energy. If one form is converted to the other form, for example, EK to EP, okay, so my EK can be converted to EP and vice versa. In this case, point X here I have is maximum EP. Okay, point W, maximum EP, and at point Y I get maximum EK. So we have what we call a simple conservation of energy, whereby EP is converted to EK. Okay, assumption here that we make, you need to take note, is that the assumption that we are looking out for is for ideal case. We are actually not looking at losses. Okay, we are not looking at losses, heat loss, or even other form of losses, sound, all this to the environment. Okay, ideal case is only just looking at EP and EK. Conversion is maximum 100%. Okay, same thing likewise when you're at the bottom, when you're at EP maximum. Okay, EK maximum at the bottom, higher speed, and you climb up, okay, to your maximum positions, you will find that, okay, the height that I can gain, okay, my EK will actually be converted back to EP again. Okay, and the EP here you are looking at is the same. It will be the same amount as point W, position W. Okay, point W. Okay, this position EP, okay, will be the same amount as the EP here, because in this case you are dealing with is ideal situation. Okay, ideal pendulum, whereby EP is converted to EK at position Y, and at position Y is converted back to EP again. So you have what we call 100% conservation of energy, whereby you are looking at is the amount of EP gained at the beginning at point W, let's say 20 joules. You'll be converted to 20 joules, but now it's in another form, EK. Then after that, you'll be further converted to another form again, to EP. How do we know this EP? Okay, the same thing that I mentioned before. When you talk about EP, you talk about vertical height. So when there's a raise in height, there's a change in vertical height, we know that the relevant energy that will change is actually potential energy. Okay, so that's what we mean. That's what I mean by when we look at the concept. We are looking at the keywords on primarily the key factors, okay, for that particular energy. Now, what about non-ideal case? non-ideal case we are looking out for is actually energy loss. Energy loss can be in various forms. It could be in the wires, in the cables, or even a simple thing like frictional. Okay, friction on the floor, or it can be by drag force, air resistance, okay, frictions along the air surfaces. So it can be various forms depending on your system. For pendulum, the most common one that we have is the energy dissipated to the surrounding, but in the forms of what? Due to your air resistance, your drag force. Okay, this is your air resistance. Okay, your air resistance. Okay, because of your air molecules in the environment, as you swing by, you actually rub against or knock against the air molecules, and this actually creates heat loss. Okay, due to friction. Okay, the drag force commonly due to air resistance. Okay, but this energy is lost to the environment. But if you look at it as a system, okay, the energy is still conserved. Okay, in the next slide, we'll look at how we actually structure the viewpoint such that in such that we still are able to explain the energy is conserved, is not destroyed, okay, or created, is actually converted. Okay, now before we move on to the next slide, okay, one thing to look at, if we talk about heat loss, same thing, we look at the keywords. When you are doing heat loss or energy loss, okay, common phrasing that we have is we just phrase it as heat loss to the surrounding, but this is not good enough, okay, to show markers that you actually understand the concept. One of the things that you need to tell the marker is the locations. Okay, example, between the surface or even the modes. Okay, it could be due to friction, or it could be friction due to the surface, or it could be just heat loss dissipated in the surrounding due to air resistance, or it could be when I'm driving, when I'm moving down towards the lowest point. So you just by simply stating heat loss is not good enough. So you need to make one more step, to include locations or even the mode of loss. Okay, to illustrate to the marker that you actually know what do you mean by heat loss. Okay, so please take note of this. Okay, the non-ideal case that we're looking for example, X, same thing, we have X, Y, and Z again. Okay, but in this case, instead of just pure pure EP converted to EK, okay, in between this system you have what we call losses. Okay, so what we always have is we actually have the initial energy, which is the EP. Okay, the initial energy, which is the EP. Okay, they are converted to another form of energy, which is the final form of energy. We call this E final. Okay, but E final includes what we call useful and useless, or useful energy and lost energy. The loss will be the heat loss to the environment, which can account for here. After that, you have the EK energy, which is the useful one. Okay, so let's say, example, if I'm looking at 20 joules at the beginning, maybe I'll get 18 joules for my EK. Then maybe heat loss would maybe account for a few percent, a minus small percent, or roughly 2 joules, such that on my left side I get 20 joules at the beginning. I still have 20 joules at the final stage. Okay, so that's what we have for my conservation of energy, and from there at EK, my 18 joules is actually converted to other forms of energy, okay, which is your EP, okay, at point Z. So at point Y to Z, the initial energy I have is 18 joules, okay, and is converted, same thing, to EP and to actually heat loss, okay, by the heat loss, and it's converted to heat loss and it's converted to useful energy. In this case, it will be EP at point Z. Okay, so for example, I have 2 joules loss again. So from 18, I will have actually 16 joules of useful energy. So in the system itself, let's say from Y to Z, you'll find that if I have 18 joules of useful energy, I will end up with 16 joules of energy. Okay, if you look at these two viewpoints, you'll find that, isn't conservation of energy not obeyed here? Okay, it's actually obeyed. It's just that in your system, for the final setting, other than useful, you need to include what is lost. So once you have done it, you'll find that actually conservation of energy actually does obey. It is present in in everyday life. Okay, just that we must know where and what to look out for. Okay, so that's one important thing that we are looking out for in terms of questions. Okay, so with this will be the last part of this first sessions of energy. Okay, it's a simple one, where primary reason is primary concept is conservation of energy. Okay, so take care.